I'm here to talk about velocity, variety, and volume, gaining insights. My name is Henrik. If you want to talk to me after this conference, please use my Twitter handle, because it's probably the only social media that I'm using at the moment. I'm a bit of an odd fellow for GOTO, at least, because I'm not a developer, but I do write a lot of code. I'm not necessarily a system administrator, but I do administer a lot of systems. I'm involved in architecture without being an architect, so I'm kind of a generalist that does lots of interesting things. When it comes to log management, my first log management solution was something I built 16 years ago, give or take, and it was industry standard centralized syslogging. A couple of years later, we did something that actually had a MySQL database backend, and that thing failed rather spectacularly. When you imagine you have a 2 terabyte database back in 2006, 2007, and you try to run all the table statement, the world just ground to a halt. In early 2011, we discovered Elasticsearch. That was, I think, just before the 0.10 release, and Logstash as well, before 1.0. And we've been running that for a couple of years. In 2013, we switched to Graylog, which we've been using for a couple of years. And given the experience that we gained doing all of that stuff, we essentially ended up building our own log management pipeline. Because I love logs, and because I so often speak about logs, I'm sometimes affectionately called Sir Logs-a-lot. I work for a public sector entity, the region of South Denmark. For those of you that are not inherently familiar with what a region does, Denmark is divided into 5 different geographic regions, and the main responsibility of a region is to facilitate the healthcare operations within a specific region. For us, that means, 14, 15, 16 hospitals, a huge number of social institutions, psychiatric wards. And while regions have other responsibilities, such as tracking soil contamination and all kinds of other stuff, healthcare is what's probably 99 point something of our entire budget. An organization this size can generate a ton of data. So I think we're logging a couple of terabytes every day. We can ingest and generate hundreds of thousands, sometimes even millions of messages per second. And we see a tremendous amount of good and really, really, really bad logging formats. What are we going to talk about today? Well, I think that we should start with a general discussion about why I think log management is important for an organization, why it is important for developers, why it is important for ops teams, security teams, etc. I will hopefully walk you through a tour of what it is we ended up building to manage all of that complexity. And I will show some hopefully interesting use cases of what we actually do with all of the data that are a bit unusual. So, why the hell should you care about log management? I have a fairly strong belief in log management being a very good tool for managing complexity. If you look at an organization of the size of ours, we have like 25,000 employees, tens and tens and tens of thousands of devices and systems and workstations and printers and drug infusion pumps and all kinds of other stuff. This entire thing actually looks a lot like a complex autonomous system. We are so big that, it's not unusual for an organization that the left hand doesn't really know what the right hand is doing, but in our size, one finger on one hand doesn't know what the other finger on the same hand is up to. And logs provide a unique insight into what is happening in this giant machinery. I mean, I've seen some of your faces go blank after going all philosophical on you. But, I mean, it all really boils down to that logs can help your organization, logs can help your development team, your administrative people running your servers, doing your security, to overcome some of the implicit challenges of such a system. And stuff is getting more and more complex every single day. I mean, how did we go from deploying our app on a single machine to all of a sudden having to manage Kubernetes? Not ditching on Kubernetes, but complexity is increasing every single day. Like I briefly mentioned, we have tens and tens and tens and tens of thousands of different devices. Some of them pretty unusable. I think the minority of you have MRI scanners and drug infusion pumps and all kinds of other stuff. But we have the usual workstations, servers, phones, and we have a presence in over 100 different locations within our little tiny part of Denmark. We need data to understand the complex interactions in our distributed system. Sometimes things can fail with no obvious reason, and sometimes an input to the system can have a radically different output than you would have realized. Data can come in a lot of different forms: metrics, monitoring checks, documentation, guidelines, but logs are also a pretty significant form of data. What is a log, really? I mean, if you think about it, it's actually pretty simple. A log is pretty much nothing more, nothing less than a record of activity. Something has happened, it gets written down in a log file. But logs are also inherently multidimensional. Compared to metrics, if you collect metrics to gain an insight into your infrastructure, you normally have a number representing a thing. So, CPU usage, memory utilization, disk I/O. Logs are multidimensional because if you think about something really simple like a log line from some web server, it usually contains 7, 8, 9, 10 different pieces of information within that log line. The request path, status code, bytes transferred, response times, perhaps even the user that was logged in doing this. So logs are inherently multidimensional. Logs are also data. Data can become knowledge if you treat it correctly. Knowledge can at some point become insight. And insight can provide a fair amount of context in terms of what is happening in your infrastructure, what is happening in your application. So what did we end up building? Well, we sat down around a table and draw some stuff on the whiteboard because we have tried this a number of times. I mean, we have tried different solutions, and all of them failed at some point due to various constraints, due to various things that we didn't even think would be interesting for us to look at. So if you look at the purely technical requirements, they were actually pretty simple. We needed something that could reliably ingest 1 million events per second. We needed something that could reliably ingest terabytes and terabytes of data. And the perhaps more interesting thing is we needed something that can work with an arbitrary amount of different formats, because we don't control the format of the data that ends up being ingested into our system. The architectural requirements were actually a bit more interesting. We wanted something that was reliable and ops friendly, because we had some bad experiences running a couple of the previous systems. That was something that was really, really interesting to us. The entire pipeline was built and maintained and run and operated by a very, very small team. So the less time we spend fixing this, the more time we can spend on our other duties and improving this little system. We wanted to encourage a high degree of decoupling, make it as microservice architecture-like as possible, because we would like to be able to grow, change, and evolve parts of this infrastructure independently from each other. We wanted to utilize modern development and operation strategies, which might come as a bit of a shock, given that I come from the public sector. That's not necessarily something most of you would think of when you think about a government entity. And we actually wanted this thing to function as an asynchronous integration platform so that we essentially could take any form of input, do something to it, and throw it into any kind of output. So essentially what we ended up with is a distributed stream processing platform for real-time events. We needed it to be optimized for high velocity and high volume. We wanted the outcome of those events to be optimized for search and analytics while allowing a high degree of variability in the input data. We wanted it to be resistant to failure, but we also wanted it to encourage experimentation so that we could continue to evolve and play and figure out new interesting stuff that we can do with all of our data. And we wanted an architecture that allows us to change almost any component without having a major impact on the platform itself. And it needed to be somewhat easy to run and easy to scale. So what did we couple together to build our little baby? Well, if you know about Kafka, if you're perhaps even already using Kafka, then you probably realize that what I've been talking about screams Kafka. How many people here know what Kafka is? How many people run and operate Kafka on a daily basis? Awesome. For those of you that don't, I will give you a very, very short breakdown of what Kafka is all about. Kafka is an event bus, a messaging system that came out of LinkedIn a couple of years ago. Conceptually, Kafka nodes, Kafka servers are called brokers. You can have multiple brokers to form a Kafka cluster. Data that gets ingested into Kafka is put into a topic. You can think of a topic like a database. A topic is then split into a number of partitions, which are the actual files that end up being on disk. And you have consumers that can read data out of Kafka topics, and you have producers that will actually produce data and push them into Kafka. Kafka can be a bit challenging if you're getting started with it, but I mean, if it's getting better and better and better with every release. And they're adding more and more features that make it more and more ops friendly. So it's actually been not as painful as we would think. We always keep a number of days of our data inside Kafka. Kafka can do, per topic, you can actually configure Kafka to say, I want to store the last 3 hours, the last 7 days, the last 2 weeks. So everything that we ship from our servers, from our switches, from our endpoints, from various appliance boxes, medical technical devices, whatever you could think of, once it reaches Kafka, it is persistent on disk. Meaning whatever else happens to our system, as long as Kafka is running and Kafka is happy, we can always recover that data. Because we have data in Kafka, we can rerun some of the stuff that we've written, some of our services, if we figure out we had a regression, if we want to play with new algorithms, then we can simply run our code and instruct the Kafka consumer client to start at the highest available or lowest available offset, and it will actually read in a day, a week, a month of production data, so that the tests we are doing are actually done against real-time or real-life production data. The theme that has been evolving over the last year is kind of this. So we have different producers pushing data into different topics. We then have a consumer group, which is a group of Kafka consumers pulling data out of that topic. They do something with that data. They then ingest that data into another topic that gets picked up by another consumer group that does something and ingests it into a new topic, and the list goes on and on and on and on until we finally hit some form of destination where those logs are getting shipped to. The interesting part about this is actually what's happening inside all of those consumer groups. Because what we ended up building is we wrote a number of small services. that can work independently of each other and do something to all of that data. Currently, we have 29 distinct services that do distinct things to our logs. And the interesting thing about microservices, because again, I'm not a developer, but looking back at the history, I kind of think microservices are a bit old. I mean, if you think about it, that command in itself could be interpreted to be a number of microservices working together to form a function. If you agree with the notion that you should write services that do one thing and do one thing well, and if you agree with the notion that you should write services to work together, and that services should be exposed to a universal interface, in this case, text streams, you have actually just acknowledged that microservices are dating back to the late 70s, early 80s, when the Unix philosophy was crystallized by Rob Pike and Brian Kernighan in a paper in 1984, which is kind of interesting. Again, we have 29 distinct services, and I thought it would be interesting to look into some of them to figure out what are we doing to all of that data that comes in a never-ending stream of different formats. We need to have some kind of event passing and some kind of normalization so that data makes sense when it comes out the other end. This particular service is written in Ruby. We utilize some of the same libraries that Elastic's Logstash does to support grok patterns, to allow us to essentially not having to reinvent the wheel every single time, because there are not of interesting log patterns out there for many of the normal log formats that you would see. This essentially allows us to map a number of passing rules to a given topic. So every message that hits is this topic, or a topic is of the same kind and would be essentially passed in the same way. We do have a few conditionals in there to allow for small variants in the actual incoming data, and to look at, okay, if we detect this string, then run this parser. If we detect this string, run another parser. But essentially, this is step one. Everything in a log gets broken down and converted to JSON. We do some interesting things. If you see this actually tells you when I started writing my slides today. Excellent example. This is a Cisco box sending some obscure syslog format, but with the right rules, what comes out the other end makes a lot more sense. You could now break down connection IDs, you can look at devices, you can filter on direction, ports, destinations, which VRF the traffic passed through. You can do a lot of interesting stuff as soon as you start breaking them down into separate fields to do searching and analytics. What we figured out pretty early in this process is that we don't really want to mess too much with the original event format. So we practice I wouldn't really call it non-intrusive, but the smallest amount of intrusion that we can get away with. In essence, you should always be able to recognize the original format. If you're used to looking at syslog events from a particular appliance box or a particular network vendor or Windows event logs, you should always be able to recognize whatever you're seeing as such an event. But that also has some inherent problems, because I think in our environment we have 12 or 13 different field names for fields that contain a source IP address. That gets really, really complex, because you have to keep all of those rules in your head about how to structure your queries depending on whatever data set you're looking at. So what we actually do is we append a number of fields to each and every log that use the same notation, the same nomenclature. So we always have source underscore IP, regardless of what is in the original event format. We always have source host, et cetera, because that then allows us for easier searching once data comes out the other end. And we always keep a copy of the original event in a separate field for various reasons. One of them is compliance. The next service that sounds a bit ridiculous is actually counting. We count the occurrence of everything you see. Every process, every DLL, every user logon, every file hash, every domain that gets visited, every IP address gets counted. And that is actually a pretty interesting problem. I've started rewriting this in C because I don't know, I felt sorry for myself one day and wanted to be really make things even more difficult. But the interesting thing is distributed counting is an interesting problem. We have a consumer group doing this, meaning we have 10, 15, 20, 30, 100 different services or instances of the same service doing counting, and doing this reliably in a distributed way, it makes it kind of interesting. Once we have a count, that actually allows us to give some context to an event. How many times have we seen this particular thing in our environment? If I'm looking at a process that gets executed 500,000 times in a week across 25,000 workstations, that's probably okay. If I see an executable executed on one machine, and that's the only time that I've seen it executable, I start to get a bit curious about what is going on. This also allows us to implement detection types such as first seen, like the first time we see something in our environment, a file hash, an exception that is inherently interesting to us. Lowercasing. It's actually a bit hilarious, but we have a dedicated service doing nothing but lowercasing of the actual field names that you're seeing, and for some event formats, even the entire event. Again, the backend that we're using for doing searching and discovery and analytics and stuff is case sensitive. So sometimes you miss stuff just because you forgot that there are some log formats somewhere that wrote something with a capital A if it's the first letter in the event. And this really helps with search and discovery and the analytics part of what it is we do. DNS lookups. We can generate hundreds of thousands of DNS lookups. A lot of the event formats that we're ingesting contain an IP address, but not the actual name of the machine doing whatever it's doing. And that, in our environment, causes a problem, because my work laptop can have 4 or 5 different IP addresses in a single workday. Wired, wireless, different locations. I start early and work from home, or I work late over VPN. We need to assign some common denominator, and that usually tends to be the name of the machine. So we have a pretty significant part of our infrastructure doing nothing but caching DNS lookups so that we don't trash our authoritative DNS servers with all of this. Entropy calculation. We have a service doing Shannon entropy calculation to estimate the average number of bits needed to encode a string of symbols. This essentially helps us to filter out names, strings that are inherently random in nature. Perfect for looking at something like DNS logs, for looking at process names, to figure out the stuff that kind of stands out compared to the rest of the system. We also do a fair amount of Active Directory lookups. Every time we see something that we can identify as a machine or as a user, we look it up and we amend a number of information to the event. Something like, where does this person work? What's their actual title? What do they do? Where is this particular machine located? For reasons that I will talk about in a minute. We have 29 of those services, like the ones I just went through, doing all kinds of interesting stuff. And the trickiest part of our entire infrastructure is actually this. If we want to maintain velocity in terms of passing 1 million events per second, we can't really wait for external connections. Stuff just, it dies. We can also kill Redis instances in the blink of an eye. So we need to be pretty clever about how many instances we run, where we run them, how we shard the data over them, because it can be quite complicated, actually. But this is essentially what helps us to maintain a high velocity in our ingest rates. And then there's this little gem. I mean, there is a reason for me losing my hair, and this is actually one of them. Time formats are probably the thing that has caused the most amount of frustration when you're talking log management. I mean, come on. The number of 100 nanosecond intervals since January 1st, 1601 UTC. Why? Why, Microsoft, was it necessary to invent yet another timestamp format? I mean, it just doesn't make any sense at all. Essentially, what all this ends up with is we built a multidimensional data model that lets us inspect and look and correlate data basically on a number of different angles and assumptions. We can look at process execution by title. Like, is the use of this application, is this process normal for a nurse working in an intensive care unit? Yes or no? We can do a lot of really, really interesting things because we have added a lot of metadata. And every layer in our matrix becomes another opportunity for understanding and doing detection and doing all kinds of interesting things. If you remember the architecture slide, we talked about being modern and being ops friendly. The team that builds, runs, maintains this is three and a half people. And they have a lot of other stuff that they need to do besides doing that. So we decided to go all in, and everything in our infrastructure that runs and facilitates our little application is actually running containers. Even though many of the people that are working on this are system administrators or security people, we try to embrace continuous improvement, continuous delivery, and a lot of the other stuff that makes application work interesting nowadays. In our particular case, we run Docker containers. We have a GitLab instance where all of our code gets stored. We have an image registry. We have a build pipeline that actually ends up deploying our images to production, so we can move fast and be relatively safe that we don't go out breaking things. And we actually have a bit of code that we have written ourselves because we have a scheduler for our consumer groups that I wrote in Ruby that allows us to introspect the consumer lag in Kafka and scale the number of consumers up and down accordingly. And hopefully, I'll finish writing the next part of this, which will actually allow us to manage Kafka partitions. So the amount of partitions a topic has is basically the amount of concurrent reads it can support. And it doesn't really do you any good to scale the number of Kafka consumers if you're not also scaling the number of partitions. But that's a tricky problem that we haven't have time to fix yet. We embrace kind of the DevOps methodologies. So plan, code, build, test, release, deploy, operate, monitor shouldn't be of any surprise to any of you. But it is interesting once you start doing this in a very, very traditional organization. Like, where do you do RFCs in there? I mean, how do you integrate ITIL processes against something like this? That's the thing, some of the things that make this really, really, really interesting from an organizational point of view, because you start challenging a number of constructs and concepts and processes that would otherwise simply disallow you to run stuff like this. When data comes out the other end, we pump it into Humio, which is a pretty nifty log management platform that is developed here in Denmark. And we use it for basically anything. Search, discovery, archiving, storage, visualization, alerting. Everything we do has Humio at its core. So while Kafka is the backbone of this application and our microservices are the central nervous system, Humio is kind of the beating heart. That's the main user interaction towards this system. We will end up having 150, 200 users once we have finished our migration process. And the security operations team alone generates something in the order of 3,500 to 4,000 queries a week. So it's pretty substantial for our security, for our operation teams. We are looking into how we can make it compliant with the different legislative requirements so that we can actually store some of our more sensitive data in there. That's ongoing work that hopefully looks like it's not such a big issue. As you notice, trending has a little asterisk besides it because I don't think that the whole Windows code has actually been released to the public, but there is something coming in terms of doing forecasting, which is really interesting. And I think we have succeeded 250, 300 different alerts that we run just on top of all of that nice data. I mean, it's great. We have a lot of events. We have structured them, we have normalized them, we have added a lot of meaning to them, but what do we actually use them for? Again, we have an enormous amount of stuff. Logs everywhere. And I would like to at least showcase two very different examples of what you can do with data like this. One of them is actually using logs for behavioral detection. Behavioral detection of malicious or unwanted activity inside your infrastructure. We run a pretty substantial deployment of Bro. Bro is a network security monitoring system that is written in Bro, the language. How many of you are familiar with Bro or Bro, the language? Yeah, my team. The interesting thing is Bro is actually a Turing-complete language that uses an event-based programming mode. It has a lot of domain-specific data types like IP addresses and ports, and extensive support for tracking and managing network state over time. The interesting thing about Bro compared to other intrusion detection systems is Bro has no notion of good or evil. Bro just reports what it has seen on the network. Bro supports a ton of different analyzers. So what Bro basically does is it detects connections, it detects the protocols that are being spoken over those connections, and then it runs protocol analyzers to basically tell you what this protocol is doing. So if it's a DNS request, you get a connection log saying somebody connected you to UDP port 53 on some machine, but you can also see what was the actual query and what was the response to that query. That all gets logged in some pretty nifty text files that are interlinked, which make them pretty interesting to use. The interesting protocol for any organization would be SMB, Server Messaging Block, which is one of the core protocols in Windows operating system in Windows networks. A lot of stuff happens over SMB, besides sharing files and printers. And we have a particular use case that I think was a little bit interesting, because let's assume that we would like to detect ransomware. Most people in this room should be familiar, or at least have heard ransomware. Some of you perhaps work in organizations that have been exposed to ransomware. It's a very, very annoying problem. When we start to talk about detection, there is David Bianco's Pyramid of Pain, which the higher you move into the top the higher you move in the pyramid, the more tricky things get. For an adversary, it is really easy to change hash values. It's really easy to modify a document or file and make it produce a different hash. It's also really easy for them to switch their attack infrastructure to using a different number of IPs, different domain names, et cetera, et cetera. What is really, really tricky for them is to change the way their malware operates. If we look into some of the data that Bro can provide, this is a pretty good example, which is actually a raw block. We have done nothing to it. Where you can see this is a rename event. Somebody renamed a file. Where you can see the name of the file, the previous name of the file, you can see IP addresses, ports, et cetera, et cetera. The interesting thing is you can now start to track different SMB events, such as file open, file read, file write, file rename, delete, et cetera, per IP address over time. Ransomware has some duties to perform. I mean, it has to encrypt the content of the file, meaning it has to read some files, it has to delete some files, it has to change the file content. Simply by looking at the rate and volume of those different operations and comparing it to a normal baseline, is something that you can start doing detection on. There will also be lots of false positives, like people starting robocopy or copying stuff around or copying their holiday images to whatever file share. But essentially, it is possible already using this single log. A file delete example, where you can start looking at, and this is probably even more useful because not many people go around deleting massive volumes of data, but that's typically something you would see in ransomware. Another interesting thing is you can see the actual file name. So if you really want to move into the typical signature-based detection thing, you could probably feed in a list of known file types. Most ransomware families have a number of file types that they use when they start renaming the encrypted content, and you can start detecting based upon that. But what's even more cool is Bro has an entire file analytics framework built in, so we can pull out files out of the network traffic, submit them for sandbox analysis, but Bro does entropy inspection. So Bro can actually help us decipher how random is the content of the file that's being written. If you start tracking that over time, you can then compare this and say, this Word document that's being written has a very, very different entropy profile to the other Word documents that we normally see in our environment. And by combining the different data types, different methods, different queries, you can actually respond pretty quickly to something that hasn't been affected by ransomware by looking at behavior and behavior only. Another thing that I find very interesting, and we're kind of back to the using logs to manage your complexity thing, is you can actually use logs to discover relationships. Most of the logs that your applications, your infrastructure, your servers, your whatever generates has some kind of notion about who is talking to what or who is talking to whom. And by modeling that, you can essentially create a graph of your entire infrastructure and of all the interactions within your infrastructure. One of the examples that we've built is using graph theory to answer a number of interesting questions. We run over 1,000 different applications. That can be anything from a small standalone desktop app to pretty substantial information systems about patients and treatments and all kinds of other stuff. And we can't remember every one of them from the top of our head. So if I have to work with or within a specific system, wouldn't it be great if I could figure out how this thing operates? You can actually do that by feeding the right logs into something like Neo4j. So you can look at this machine, the clients connect to this web front-end server, this web front-end server talks to that database, and that database actually also archives files to that file share, which is inherently useful because you kind of create a self-documenting infrastructure. You could then start to look at what impact do actual changes to your infrastructure have. How many people here are developers? How many people here do microservice-based architectures? How many of you actually know exactly the number of upstream and downstream services that are dependent on your code? This is one of the things where graphs actually can help, because you can model the entire dependency chain across your distributed application by using the logs that already exists. And it doesn't have to be as hard. If you look at something like Neo4j, it is inherently easy to express some of those changes. And what you end up with is something pretty that can be inherently useful. This is kind of the current state of affairs. This is what we have been spending, I don't know, a year on, because we have a lot of other stuff that we have to do also. And if we look into what we will most likely be tackling in the future, we will expand our usage of Kafka. We have run some interesting experiments around K-streams and K-tables by manipulating the actual partitioning keys that data gets partitioned over. We will most likely be able to join disparate sources of data and key them on a common field, like getting an event stream for everything that a specific user or machine or service application has done, despite where those logs are coming from. And we can then turn this into a table to obtain a real-time view, essentially a aggregated, materialized view that we can update every 10 minutes, 15 minutes, 30 minutes, that can help us to manage some of all of our data. And exposing the new KSQL interface so that some of the people that are perhaps not as used to some of those technology can actually work with some of that data using something they're familiar with, like ANSI SQL. And we will probably also start to look a bit into machine learning. We build a highly multidimensional data model, and there are some algorithms that are very good in terms of working with that. Something like k-means, which is inherently useful when you're talking multidimensional data models. And that can potentially help us with doing outlier detection and other interesting stuff. AI is not something we've dabbled with because machine learning is where we kind of draw the line. That's what beyond that, it is something that's not really territory that we would like to venture in because we really have no idea what we would be doing. That's essentially all I had. I hope it was useful. I hope it was interesting. Are there any questions?
Henrik, there's one question here through the app, so I'll fire that out now. Have you made any considerations concerning the forthcoming GDPR? That's the General Data Protection Regulation.
Yeah. Yes, we have. For organizations such as ours, that's actually a really big problem because PII and PHI is pretty much everything we touch is in that category. And this is also why we have decided to keep all of this on-prem. So nothing ever leaves our infrastructure. It runs on dedicated infrastructure that is only accessible by very few people in our organization. We have made sure that everything we do has an audit log. Even every query inside Humio actually gets logged. So we have a separate organizational role that can go in and figure out who has accessed what data and for what purpose. And we are working with them at the moment to make sure that even the data on disk is something that can't really easily be compromised. So even I, as an administrator, can't SSH into that thing and start deleting some of the queries that are generated. But because we run it on-prem, because we have a very limited exposure, because there is a permission model that controls exactly who can see what data, many of the GDPR issues are actually not such a headache for us.
Thank you. Any questions from the audience?
Hi. How do you handle sensitive data within logs?
How we handle sensitive data?
Do you mask it or?
We have certain types of data that we run anonymizers over. We also make sure that data that contains sensitive material is removed within the required time frame, because we can actually store some of this for a shorter time in terms of debugging and other stuff. So there are a number of guidelines that we do, but we would actually rather remove data than anonymize data, because most of the key fields that we use for analysis are the fields that we need to anonymize. So that it doesn't make that much sense. Then we would rather expire data and say, okay, if you only can keep it for a week, we only keep it for a week.
Okay, so you haven't had need for encryption or opening that encryption during the...
Not at the moment.
Okay.
And mainly this is about infrastructure logs, security logs, helping to find faults in different devices and appliances and all that stuff. The next giant leap will be offering this to our business as a service. So going out to the clinicians, going out to the people running the applications, and having a discussion with them about how we can help them achieve some of the, even some of the GDPR things around that you actually have to document that you check the access logs for your application, stuff like that, where we are in a unique position to offer a shared service that can help with that. But it's only then when we start to hit the tricky issues.
Okay, I have another question as well. How long you have been doing this? You said that you have 29 different microservices.
We started this journey, I think, a year and a half ago. It's when we started feeling the growing pain and some of the constraints of the trade-offs we made with the previous iteration of this system, we started looking at how can we do this better, how can we do this smarter, and how can we solve some of our problems. And I bet you that in a month, in 2 months, in 3 months from now, this system will have changed in some way. And that's an inherent thing that we built into the system, is the ability to change, to grow, to learn, to fail, to relearn, and to do other interesting things that can help us achieve our goals.
Okay, thanks.
Any more questions?
Cost.
Drop the mic.
We spend taxpayer money. So our foremost obligation is to make sure that we spend taxpayer money correctly. The majority of the stuff that I've been talking about is actually open source. It's either open source or it's something that we developed. It was a conscious choice, even though we have an operating budget of 24.1 billion, the majority of that goes into healthcare. And even if we could go out and buy a support contract for something like Kafka, we are under some very, very interesting purchasing rules as a public sector entity, and we kind of want the core of this system to be free. We wanted something that even if we have to do a public tender and somebody else wins a bit, we can change the different parts of our infrastructure without changing the core of it every single time. Imagine if you need to do a public tender, if you have somebody coming in and underbidding the competition, and you every 3 or 4 years have to change the entire system. You have to port all of the rules, all of the alerts. It gets really, really cumbersome. The stuff that we are paying for is some of the stuff that we simply couldn't do better ourselves. So we have some endpoint telemetry sensors on our workstations that log all the DLL loadings, process executions, registry writes, files that are getting accessed, all that stuff, and we have Humio. And both of those are actually a lot less expensive than you would think. Was that politically enough answered?
Any more questions?
What was your major driver to move from Elasticsearch to Humio?
That's an interesting question.
Somebody said Elastic sucks over here.
Like I said, we have been running Elastic for 5, 6. We still run Elastic. I mean, we still have parts of our old infrastructure that we haven't moved into this pipeline yet, because we have actually 150 people doing service desk work that use the system every day to figure out why the hell somebody's account keeps getting locked out. Those people need to be retrained. We need to get them into the new system. Those operations take time. Essentially, we moved from Logstash to Graylog in 2013 because Logstash has some inherent issues around availability. There wasn't really no way to introspect the system to figure out what the hell was going on. It kept failing and kept throwing away data. So we replaced Logstash with Graylog. And we've spent more time managing Elastic over the last year than developing this entire pipeline. When you start to move into the realm where you have racks of Elastic servers, you often also need people that are trained to handle that system. If Elastic is part of your application already, I mean, if you use it for low latency search for something else, then you probably have people who have a good idea about how that thing works. But for a logging specific purpose, it was simply a piece of software that could do too much, because we inherit all of the complexity, because Elastic can be used for anything from doing logs to chasing Ebola outbreaks in Africa. The third thing that made us change was the inherent trade-off in most of the systems that we look at in terms of velocity and volume are always centered around the notion of, are you doing schema on read or schema on write? In our Elastic cluster, 80% of the resources are being spent by maintaining indexes for search. Humio has a rather different approach because they don't do much indexing, they do brute force searching. This allows us to have a relatively small amount of resources that can ingest even more data than our gigantic 3-rack Elastic installation. I mean, the switch alone, I think we saved something like 100,000 euros in hardware and licenses and stuff by making that switch. So for us and for our specific use case, it was the right choice. Elastic is a great product. I like what they're doing, but it just wasn't the right choice for us.
Thank you, Henrik. Unfortunately, I think we're out of time now. So, yeah, thank you very much.
Thank you for listening.